OK, so we're kicking off the industry lab section here. Our first speaker is Andrej Karpathy from Tesla. Thank you.
OK, hello, everyone. I'm super excited to be here. I've actually been a long-time user of Torch back in the day, and then I briefly flirted with TensorFlow for a while. But when PyTorch came out, it was kind of like love at first sight, and we've been happy together ever since. So it's really exciting to see that it's really maturing and attracting a large developer kind of community, and I'm really excited to be a part of it. OK, before I dive into my talk, I would like to briefly thank Sanjeev Satish especially, and a lot of other people at Tesla who have really laid all the groundwork for everything that I'm going to talk about today. So in particular, I'd like to talk about engineering practices for software 2.0. Now, just to break this down a little bit, all of us are training neural networks, and we're training neural networks. But actually, I'd like to argue that what's going on is actually much deeper than just training some machine learning models. I think what's going on is that we're actually fundamentally changing a programming paradigm. We're introducing a new programming paradigm and working with it. So just to break down the term a little bit, normally what you would be familiar with is you want some kind of a program that performs something that is desirable for your application, and you would just specifically write the C++ code or JavaScript code or something like that. And instead, what we're doing now with machine learning is that we are instead defining a set of programs that we are going to search over. Then we introduce a data set that kind of constrains or gives like soft constraints on desirable behavior of the program. And then we are using optimization to actually like write that code. So stochastic gradient descent is really writing the code, and that code is in weights of a neural network instead of something like C++. And so a lot of these models that are kind of written in this new programming paradigm are kind of taken over. And a lot of the 1.0 code that we've seen and worked with so far is now being transitioned into the 2.0 stack. And so these two code bases really like meld, and you can port functionality from one to the other. And so in particular, the point I'd like to make is that this is not just like training an imagement model or something like that. When you are working with these networks in production, you are doing much more than that. You are maintaining the code base. And the code base is alive, just like the 1.0 code. In particular, you have new feature demands for the 2.0 stack. The stack contains bugs, and you need to clean them up. And this code base really requires iteration and love over time to get it to work in your application. Except the knobs that you have with respect to programming in this new stack is you are not writing the code to actually fix your bugs, but you are iterating on the data set, you're iterating on the model class, and you're iterating on the optimization that you're using to actually train your model. So we use these neural networks, of course, extensively at Tesla in production for the autopilot. And we're working with a lot of neural networks and putting them in production. And what's really important and interesting for us is to talk about the kind of engineering practices around how to work in this new paradigm. So in particular, we know what the best practices are for the 1.0 stack. And viewing machine learning through the lens of programming immediately suggests kind of analogies between how we can take the best practices from 1.0 code and port them over to 2.0 code. So in particular, I'd like to go into a few examples. One thing that we're finding is extremely interesting is this notion of test-driven development. So traditionally, what you would do is in test-driven development framework is you would write your test first, and then you would write the code that implements those tests. And we want in the 2.0 stack, we're training neural networks, and we want to kind of adopt the same framework. And what's interesting is that you might think naively that this is your test set. Your test set is kind of like the unit tests. But you have to be very careful because your test sets normally are constructed in a very naive way. Like normally, ideally, you would take a data set and you would split it like 90-10%, and your 10% of the test is your test set. And the problem with that is that what we are finding is that your test set is actually extremely important and should be manually curated and extremely rich, varied, and clean. And it's really important because we aren't just interested in the expected performance of that model. Like when you are working in a test-driven development framework, you are not writing your unit tests that say something along the lines of your code works 90% of the time a little bit. Like that's not the kind of unit test that you have. You have a complete unit test coverage of your program, and you're trying to like especially care about the edge cases and around your code and really cover all of these possible edge cases. And so we find that the same is true for the 2.0 stack. We actually massage the data set, and we care a lot about all the edge cases. And especially, for example, when you find a bug in your code, that kind of corresponds to a neural network that does not make a correct prediction. And so what you are going to do in that case, if you find such a mistake, is you want to take that mistake and incorporate it into a unit test, and you want to make sure that that is covered in the future. And then the way you actually go about fixing that problem, of course, is not just by writing code. You go about fixing or completing that unit test by either incorporating more examples, most commonly, or by changing the model architecture, or via the optimization. But you can kind of adopt the same framework, and really what it means is you have to care a lot more about your test set and massage it carefully. I'd like to also talk about the concept of continuous integration, which is very common and useful in the 1.0 stack. So in particular, the traditional CI workflow would look as follows. You would try to automate your build. You would like to make sure that you always run and kick off your unit tests. And for every commit you submit, you actually want to immediately test your unit tests so that you can spot bugs if you introduce them. You want the build to be extremely fast, so this can run on all the commits, for example. And you want to make it easy to kind of deliver releases and things like that to other people. And you want to potentially automate the deployment if you trust your unit test coverage enough. And so all of these actually have an equivalent in the 2.0 stack. In particular, if we're talking about automating the build, in this case, the build is really the optimization. You want to train your neural network. And that basically takes your data set and compiles it into weights. And so it's kind of just like neural network training. You want to run the unit test immediately as in the 1.0 stack. Every commit should be built. In this case, the subtle issue is that not only do you have your PyTorch repo or something like that, where you have commits into the PyTorch repo, but actually the data set is now part of your code. And any change to your data set, which is something you'll be doing very often in any kind of production environment, because you're adding labels, subtracting labels, or adding data sets and images and so on, those are all commits to your code base because they influence the final code. And so you actually have to keep track of this and rebuild every time you change your training set. You want the build to be fast, so of course you want to use, say, large-scale distributed training, and you want to make sure that you minimize your walk clock time of training the network. Make it easy to deliver the latest and greatest. We keep a pretty comprehensive model zoo internally for ourselves, and that's something you want to do. And of course, you want to automate the deployment if you trust your unit tests completely. The other thing that I find interesting is in version control. So of course, we all use and love version control, like Git or something like that, for our 1.0 stack. But again, in this paradigm, version control actually extends to data sets. And so you actually want to do version control in data sets, and we think about this quite a lot at Tesla. So in particular, what's interesting is most of the programming is by adding data of certain type. And so anytime you add data, you're changing the code. And what's kind of complicated is that your label set and your image set actually change over time. And so you really want to think of every single change to a label as a commit. And so we are very careful with our data labeling team, how they label our data. And every single commit that they make by putting bounding boxes around things and so on is carefully tracked, timestamped, logged, associated with the user, et cetera, because we actually want to really think of those as commits to a code base. And treat them as kind of first-class citizens in the entire kind of approach. And finally, the concept of monorepos is also kind of interesting. Monorepos are basically these giant repositories that big tech companies often use, such as Google, Netflix, Twitter, I believe Facebook as well, not 100% sure. And really, the benefits here are that you are sharing all the code base, all the dependencies, and you are simplifying the dependency management. And we kind of find that there are similar equivalents to that when you're working with the Software 2.0 stack. So in particular, you want to kind of have a single code base, which is kind of like your neural network, and that supports many different tasks. And what's very tempting to do in a production environment is that people like to take those networks and they like to fine-tune their things on top of the network. And so I take the network, that's a release, I fine-tune my own task, someone else takes that and fine-tunes their task, and you end up with this kind of chain of fine-tuning, and it just kind of can very quickly disintegrate. And so you have to be very principled. So what we find is, because those are equivalent to basically different repos. So you want to make sure that everything sticks together. You retrain your network from scratch every time and maintain a single model. And we find that this is also incredibly helpful in working with this stack and eliminates a lot of headaches. So in summary, I'd like to argue that we should treat deep nets like code, and we are able to borrow a lot of ideas from good software engineering practices from the 1.0 land to the 2.0 land. So in particular, we adopt a lot of test-driven development, CI, version control, and we like to automate all of this and really have a broad unit test coverage and really think of this as programming, except you're just not writing explicit code. You're iterating over the dataset model and the optimization. And so I think collectively, since this is so new and people that aren't used to thinking of this as programming, it's really just, we're barely just scratching the surface, but I think collectively it's exciting to really explore what the best software engineering practices are for iterating on this code and programming in this new paradigm. So yeah, that's it. Thank you.
Hello, everyone. I'm Brian Catanzaro, and I lead applied deep learning research at NVIDIA. I'm really excited to be here and share the joy of PyTorch 1.0 with all of you. We're really big fans of PyTorch in my group and at NVIDIA, and so I wanted to kind of talk about that. Now, they told me not to give a GPU sales pitch, and I promised I wouldn't. But I did want to say I love GPUs, and I'm really excited about the future of custom hardware for AI. My talk's actually going to be about what we're doing with PyTorch at NVIDIA to make our products better, to find new ways of using deep learning that makes NVIDIA products more interesting and NVIDIA more efficient. So Andrew Ng has this idea that the limiting factor for progress in research is the latency of generating an idea. And the way it works is that we come up with a new idea. Every one of you wakes up in the morning with a whole bunch of new ideas. You have to test your hypotheses. You have to write it up in code. Then you have to run some programs, train some models, do some evaluations, and that tells you what's wrong. It gives you some new ideas. And then you can iterate on that. That gives you new ideas, right? And so there's a cycle that we go around. And as we're working on research, the latency that it takes for us to go from idea to idea is really what gates progress. And PyTorch has been an incredible tool for us to reduce that latency. I think it's simple, it's easy to get started. It's also fast, so when we're training our models, we can train them fast. And it's also extensible. At NVIDIA, we're always inventing new kinds of kernels, new kinds of GPUs. We need to figure out how they're going to work. And it's really great to be able to plug our latest code into PyTorch, just extend it and get started. And so that's one of the reasons why we spend a lot of time doing PyTorch at NVIDIA. And all of the projects that I'm highlighting today were all implemented in PyTorch. They're all trained in PyTorch, and so I guess they're PyTorch native projects. The first one is called deep learning super sampling. So I don't know how many of you saw we released a new GPU a week or two ago. It's called Turing. The architecture is called Turing. And one of the things that's really amazing about it is that it has tensor cores throughout the whole lineup. So we have really high AI throughput, even in consumer GPUs that people are using for video games. So that begs the question, what can we do with AI to make real-time graphics better? And deep learning super sampling is one of our first attempts to do this. We're really excited about it. I don't know, it's probably too dark to see on the slides here, but there's a lot of reviews on the web where you can go out and actually compare the pixels between a traditional way of rendering graphics and the deep learning super sampled way of rendering graphics. And the thing is that we can use neural nets to do super resolution and to do aliasing removal, make the pictures look better, make the game more interactive because it's actually running faster thanks to the power of tensor cores. And so we can now apply deep learning to real-time graphics, and that's pretty exciting for us. Wouldn't have been possible without PyTorch. We have a large team of people that are constantly iterating on this, training new models, evaluating different loss functions and the standard things that you do when you're working on a deep learning problem. And PyTorch has really made that possible. OK, the next project I wanted to talk about is in-painting with partial convolutions. And you'll forgive me for working on Ernest Borgnine's face over here while we talk. The idea here is, can we actually edit images with a smart retouching brush that can remove things that we don't want to see in the image and replace them with content that's plausible semantically? So with Ernest here, I'm going to crop out his eye. It gave him some new eyes. Now, those eyes actually, the reason the model knew how to draw eyes is because it was trained on a database with lots of people in it. In fact, trained on the Celeb A face dataset, some of you guys may know, which has a lot more women in it than men, which is the reason why his eyes ended up looking the way they do. But the thing that's really cool is that we're able to use deep learning to actually understand the semantics of an image and what content should be synthesized in order to fill in the gaps. There's a demo website, research.nvidia.com/inpainting. You guys can pull it up and try it on your own photos. So here's another one we're really excited about, image and video synthesis. This is open source on GitHub, and it's also published at CVPR and NIPS this year. And the idea is we're replacing the traditional graphics rendering pipeline with a generative model. So all these faces right here, the input is on the left. It's a very high-level representation of the scene. And then the output is on the right of what's coming from our neural network. So we can go from edges to faces, or we can go from poses to people. The idea is that it should be something easy to create. We can have a simple graphics engine that maybe just creates edge maps, or maybe it just creates poses, and then we can use that to actually be the input to our model. That should make it possible to create new virtual environments much more cheaply because we can train them. It's a data-driven approach to creating a virtual world instead of a sort of manual artist-driven approach. And we're really excited about, what does it look like to make a game where the whole game is being rendered by a neural net. Let's see if I press this clicker if something will happen here. OK. Here's another project that we published a couple weeks ago at ECCV, which is on frame prediction. On the left is a ground truth video, and on the right is a video where every other frame is being predicted given past frames. And basically, this is a neural net that takes in as input the sequence of past frames as well as some optical flow, which we're using FlowNet2 to do that. And then we predict for every pixel a vector that says where from the source frames should we take our data. And then we also predict a sampling kernel that we use to convolve the past frames with in order to produce the output. And we're really excited about these results. Obviously, there's a lot of ways that we can use frame prediction to make video games look better. OK, some other projects, text-to-speech. So WaveNet, I don't know how many of you have ever used WaveNet before, but it's this really cool model for generating audio samples. It came from DeepMind. And it has really high quality. A lot of people are interested in deploying WaveNets. One of the problems with that is that the inference procedure for WaveNets is very sequential. And for a while, people actually thought it wasn't possible to do them on GPUs. In fact, there were some papers published that said we tried really hard, and it was running slower than real time on a GPU, and even at a batch size of 1. So that was kind of disappointing, but some people at NVIDIA had some ideas about how to improve that, and we actually created a new WaveNet inference implementation that can run 320 voices of the deep voice net from Baidu Deep Voice paper at 16 kilohertz. And actually, it could actually go up to a maximum sample rate of 48 kilohertz, which is pretty good. And so we went ahead and open sourced PyTorch implementations of both Tacotron 2, which is the part of them. Tacotron 2 basically takes as input text, and then as output is a MEL spectrogram. And then we can go use the WaveNet to go from that MEL spectrogram to actual sound. And so those are all open source on GitHub, and they're all PyTorch native. OK, so the last thing I wanted to highlight is this project that we have going on unsupervised language modeling. On the right, you can see some tweets about our new GPU. Our marketing department is always interested in finding better ways of understanding sentiment online, figuring out what people are saying about our products and our company. And there's this great idea from OpenAI, from Alec Radford and some other people with this idea of training an unsupervised language model on a large amount of text, and then using that as a feature extractor to solve concrete problems like sentiment analysis. And we really liked that idea, so we went ahead and reproduced their result and open sourced it at the URL above. And we were able to take the training time for this unsupervised model from a month down to about 4 hours by using mixed precision arithmetic, FP16, FP32, on 128 Volta GPUs. And we also, so once you have that language model, it can be used for a lot of different tasks. But for example, you can use it as a feature extractor, and then with a small amount of labels, you can train something like sentiment analysis. And so that's what we've done, and it's been really helpful for our marketing team to have access to better sentiment analysis. One thing that I wanted to mention about this work is that we used PyTorch extension called Apex to do the mixed precision training. One of the problems that people have when they're trying to get started using mixed precision is that some operations are unsafe. Like, for example, batch norm. If you do batch norm in FP16, you're going to run into all sorts of numerical problems because batch norm is a little bit finicky. And so what AMP does, it's a part of Apex. AMP actually has a white list and a black list of different parts of a neural net that should be done in FP16 using tensor cores on Volta GPUs or on Turing GPUs, or which parts should actually be done in FP32, and then it will automatically insert the appropriate casts to make your model safe. And so when we were working on this, we used this, and it really helped get us to a safe, fast implementation using mixed precision. So that's it. I just wanted to highlight these projects. NVIDIA is doing a lot of stuff, applying deep learning to a lot of different projects in a lot of ways, and PyTorch is at the center of all of it. Thank you.
Hello, everyone. My name is Brian McCann. I'm one of the research scientists at Salesforce Research, and I focus mostly on transfer learning and multitask learning in the context of natural language processing. And I'm excited to share some of our most recent work in multitask learning for NLP. We call it the Natural Language Decathlon, and just kind of walk through our approach, kind of what we did, and give you a sense of the code that we put out there. Everything's in PyTorch, so you can get a sense of how to get started with it. This project really came out of the observation that we as a community are really good at taking a single task and designing a model for that single task. And as long as we have enough data and a concrete enough metric, we can hill climb on that. And we can get to human performance in a lot of cases over the course of a year, maybe 2 years. But then when we have another task that comes along, a new data set, or something like that, we mostly start over. We have some pre-trained word vectors, maybe some contextualized word vectors, but a lot of things just start over from random. And a lot of the design decisions, the things that we learn about the modeling process, don't necessarily carry over to other kinds of tasks in NLP. So from our perspective, we wanted to explore the idea of making more general NLP systems. And we see multitask learning as a blocker in this setting. For us, we can use language to do a lot of different things, gives us a lot of flexibility, but our models don't necessarily have this. It's quite difficult to get them to share experience and knowledge with each other. So the Natural Language Decathlon, or Deca NLP, as I'll call it sometimes, you can think of this as a benchmark for multitask learning. And then I'll talk a little bit about it as a framework and our approach to the decathlon as well. We can start out as the benchmark. This is kind of the easiest way to think about it. The decathlon is, well, a set of 10 tasks. And it's a set of 10 quite disparate, fairly difficult tasks. Things like classification are in there, but also tasks that require generation, like machine translation. You have to do question answering, abstractive summarization. And the challenge here is that really the one thing that we really know in multitask learning is that related tasks tend to help each other, and unrelated tasks tend to hurt each other within a single model. But again, this is, we chose diverse tasks because we want to tackle this problem. We see this as a blocker, and we want to make progress on it. So the decathlon allowed us to measure progress on this and helped guide our design decisions. You can check out the website for more information about any of the specific tasks. There are 10 of them, and I'm not going to get into the specifics of each. But you will also find that we have the leaderboard, where you can find the performance of the current decathlon champion. You can see a breakdown by task, and then you can also see a summary score that takes all of the different metrics for all the different tasks and just adds them up and sums them up into a decathlon score, so that we can use this to determine when we make changes that maybe help question answering but hurt translation. Is this something that's really worth doing overall? Is this a general change that we're learning about in the modeling space, or is this something that's just helping us on that specific task, or maybe even just that specific data set, or takes advantage of a specific quirk of a kind of data set? The more exciting kind of in the PyTorch setting is the framework and the code, the models that we released around this work. And this really centers around DecaNLP as a place where you can study multitask learning the way that we did, but you can also study things like transfer learning, zero-shot learning, domain adaptation. We spent a lot of time thinking about different training strategies and working on optimization strategies. So even though multitask learning is kind of the core focus of our benchmark, the framework that's around it is really useful for all of these kinds of things as well. And just as some examples pulled out, it's very easy to train on a single data set, like the Stanford question answering data set, Squad, but you should also be able to seamlessly switch between single task learning and multitask learning. So you can add translation tasks in there. You can add all 10, of course, and it's really easy to train on the decathlon, explore different training strategies. And I would really encourage you to kind of dig in and see how easy it is to all of a sudden try out your models in this multitask setting. Of course, it's also easy to evaluate. We wanted to make that as easy as possible. And with these tasks, everything tends to have its own metric. There's blue for translation, maybe rouge for summarization, classification accuracies, F1s, normalized F1s, logical form exact matches. We wanted to package all this up so that everybody could have access to this super simple, and you can just run things in one command and evaluate your models. And we also wanted to package up our pre-trained models, because in the research that we found, the models trained on the decathlon ended up being better and more efficient at learning new tasks, like new language pairs. We trained it on English to German translation, but if you wanted to train it on English to Czech, the decathlon trained models will actually be better as pre-trained starting points, but over like random initialization when you're training that, or if you're training a part of speech or NER model on top of it as well. And what's fun about this is that you can also add your own custom data sets fairly easily as well. It's just simply a JSON file, and all you have to do is somehow formulate your task as having an input, like a context, maybe a question defining the task, and an answer as well. And that's all it is. You can add this into the decathlon and see how your task interacts with all of the other tasks there. You can try our pre-trained models out on that. And this is kind of hinting at the approach we took, which was really a kind of a combination of a sequence-to-sequence and question-answering approach to our model, where the encoder side looks a lot like a question-answering model, but the decoder side is generative and outputs words one at a time over many time steps. This allowed us to unify things like classification and generation, and it allowed us to get things running on all 10 tasks. It also kind of conveniently got us good performance in the single task setting for some tasks as well, even though we weren't designing specifically for those tasks. And we set ourselves as kind of the extreme case and the extreme constraints where we wanted to make sure that the model didn't have any human intervention. There's no task-specific settings, or all the parameters are shared all the time. And this really gave us the ability to do some interesting domain adaptation and even some zero-shot behavior. And to kind of give a sense of what this looks like, I want to switch to a live demo. So we'll see if we can get this up and give you a sense of what this model looks like. So because we have our pre-trained models up there nice and easily, we just wrapped. This is a research demo. It's not a product demo. So it's just wrapped up in Docker and then wrapped up in a web server. And you can do things that are fairly intuitive. So question answering is one of the tasks that we have in the decathlon. So you can look up basic Wikipedia pages, and you can use the URL here for kind of brevity purposes. And you can ask things like, what is PyTorch? And as long as the internet holds up, we'll find out that, OK, PyTorch is an open source machine learning library for Python. And what's nice about this is that we can also demonstrate some of the other decathlon abilities, like PyTorch 1.0, big exciting development. And if we look at like a press release for this, we can do a few things that are kind of interesting here. We're just going to post the URL again, and then we can ask things like, is this sentence negative or positive? So this is pretty unnatural, and for us, this is the the question that we used when we were training sentiment classification. And as long as I didn't make any typos there, you'll see, OK, this press release is, I guess, kind of positive. But what's nice about this approach is that we can do the same thing, and we can actually switch up the question. Even though we didn't train on questions like this, because the model is learning to use language more generally, we can try some more interesting things, like, is this release pessimistic or exciting? And finds out it's exciting. Even though it hasn't really learned or trained on anything like that, it knows that it can use the question to constrain its answer space differently. And there's lots of interesting things here you can play around with. I would encourage you to try out our pre-trained models and see where this breaks. But for now, I'll just switch back to the slides and mention that this multitask project is kind of part of our dream of maybe one day developing a multitask model in research for lots of different things, and then deploying that single model into production. And that's how we see it fitting into PyTorch, giving us the ability to streamline that process, because currently it's kind of difficult. But if we could have a multitask model and deploy that single model for many things, that could make things a lot more interesting in the long run. Thanks.
Hi, I'm Fritz Obermeyer, and I'm going to tell you about Pyro, which is a deep universal probabilistic programming language we've built at Uber AI Labs. This is the Pyro team. We have 5 core research scientists and engineers, and we're led by Noah Goodman, who's a Stanford professor. We built Pyro to be a platform for research in modern Bayesian machine learning methods. And in these methods, neural networks are often used both in modeling and in inference. Our goals in Pyro were to be universal, scalable, flexible, and minimal. Most of these or a lot of these are achieved just by building on top of PyTorch. PyTorch is a great platform to build a probabilistic programming language on top of, both because it has AD, dynamic compute graphs, and it's built on Python. We also achieve scalability by targeting machine learning methods that allow data subsampling. To achieve flexibility and minimality, we've built a 3-layer architecture where we have a probabilistic programming language interface, an effects handling library that's mostly used internally for non-standard interpretation of the language, and then a set of inference algorithms on top of the effects library. The language consists of just a few primitives that are on top of, can be inside your Python programs. Then the effects library has a number of effects that allow the non-standard interpretation. And by having the effects library in between, we can build composable inference algorithms and inference algorithms that can be embedded within each other. And it's really nice for developing fancy inference algorithms. So let's look at the ergonomics of the Pyro modeling language. The basic statement is the Pyro sample statement. Here, you can see that at the top, we sample a number x, or a tensor x, from a Bernoulli distribution. So this Bernoulli distribution is just part of the Torch distributions library. And in keeping with PyTorch's convention, Pyro has eager semantics. So the x is actually a tensor. It's not a random variable object. It's actually a tensor. And the second line here, you can see that the observe statement is like a sample statement, but when you're conditioning on data that you've already seen. The third statement is a declaration that a particular part of your program is differentiable or optimizable. And we can also optimize with respect to constrained parameters by specifying a constraint, and the constraints are just part of the PyTorch constraints library. We also have a couple language constructs to express statistical independence among variables. So these can be either statistical independence among variables that are packed into a tensor, and we wrap that in a context manager object called IRange, or they can be statistical independence among objects that then have different dynamic downstream control flow. For example, if we have compute graphs in different branches or different indices of a for loop, and we wrap that in a generator. So how do we wrap these primitives up into a model? In Pyro, a model is just a Python function. Here's a model where idiomatically we pass the data in as a parameter to the model. In the first line, we declare a parameter, and this parameter will be differentiable. In the second line, we can sample from a distribution that depends on that parameter. In the third line, we have some control flow and some observe statements, and we can even use helper functions. Here you see the helper function below. And by building on Python functions this way, we can leverage all of Python's great organization of code and create large models that span multiple files or multiple teams in an organization. So here's an example of a more complex model. These models you can think of them as generative models of data. So here's an example of like an MNIST digit generating model, where it's like a VAE, but we've disentangled the latent variables of style and the digit that we're generating. So first we define a decoder network. This is just a PyTorch NN module. And we can declare that module in Pyro with a pyro.module statement. That's just a fancy pyro.param statement that recurses through the parameters of a module. And you can see that we have a couple sample statements, and then finally sample from a Bernoulli, an image that depends on the style and the digit. So whereas the generative model used a neural network to generate data, we also use inference networks. Here we call this a guide, which is just the inverse network. And just like in a VAE, this uses a neural network to infer the latents given observed data. So the guide also inputs the image, and we have two different encoders, one encoder for the digit and one encoder for the style. We can call the digit encoder based on the image, and then conditioned on the digit and the image, we can infer the latent style. And the latent style can be all of the messy embedding parameters, whereas the digit has a nice interpretation. To train one of these Pyro models with both a forward and an inverse model, we can use stochastic variational inference. This is the most common inference algorithm we use in Pyro. Here we create a stochastic variational inference object with the model, the guide, an optimizer, and a particular loss function. Here we're using the elbow loss, which is like a KL. And then we can train the model using just Atom or SGD, using mini batches of data. Once we've trained the model, we can then use the inverse guide. This guide for serving predictions, we can use it as a classifier, or we can even pull out one of those encoders as a classifier and use it completely independently of Pyro. So this is just a rough map of the Pyro and PyTorch architecture. And I want to make 2 points here. One is that we work really closely with the PyTorch team on the distributions, transforms, and constraints library, the Torch distributions library. And that integrates very closely with Pyro to make Pyro models broadcast correctly and deal with and fully support the PyTorch JIT. The other note is that users and application code typically write users typically write three types of code. One is just the models that we saw before, these generative models and the inference networks. But there are also two other types of code. One is custom inference algorithms, and these can be composing, say, local inference that uses second-order optimizers, maybe multiple steps for local variables, and then some other global optimizer for global variables. So one is custom inference algorithms, and another type of code we write is distribution objects. So distribution object is it has sample and log prob methods, but and together these allow you to wrap arbitrary Python code for use in the probability monad, so that you can use it inside Pyro programs. So we tend to write lots of different custom distribution objects. These can be hand-coded feature models, or they can be inference algorithms that use some other inference method that isn't just SVI. So if you're interested in learning more about Pyro, check out pyro.ai or stop by our poster. The whole team is here today to chat with you. And we'd like to thank all of our open source contributors and thank the PyTorch team in particular for lots of help getting Pyro to work well with the distributions library and the JIT compiler. So thanks.
So, hi everyone. My name is Mark, and I'm from the Allen Institute for Artificial Intelligence in Seattle, where I do kind of research and engineering. And I'm one of the lead developers on Allen NLP, our platform for deep learning for natural language processing. So, we kind of had this vision when we were deciding to build this project that we wanted to create like an open source library with the most useful deep learning abstractions for text available for anyone to use. And kind of part of that was building great reference implementations of standard models so people could pick them up and run with it, and also use them as kind of black boxes. If you want a dependency parse, you can come to LNLP and know that you're getting a state-of-the-art model. Also, we had in mind that we wanted to be able to leverage research that we were doing in word representations, in this case, particularly ELMO, which is a method for using language model pre-training to develop contextual embeddings for sentences, and be able to leverage those easily across lots of different natural language processing models really easily. And then also, we just wanted a framework that would allow us to continue to drive our research forward on paragraph understanding and semantic parsing. So we actually originally built this framework on top of Keras, and then we rebuilt it on top of PyTorch. And you kind of heard a lot about the first two already today from kind of almost every speaker. But one thing I don't think has been particularly noted enough is that we found the PyTorch community really kind of engaging and active, and really eased our transition to PyTorch when we decided to make the switch. So we were kind of, you might be thinking, right, so you chose to use PyTorch. Why didn't you just start building models in PyTorch? Why do we need kind of an extra framework? Well, one main thing was we were really jealous of the reinforcement learners who had these crazy demos of people doing backwards rolls to run really fast. And we wanted our own kind of high-quality demos which people could play with and figure out how these models break under various different assumptions. We also found the kind of batching and padding a little bit lacking, because we really wanted support for structured data and nested data. In some of the semantic parsing work we've been doing things like embedding grammars, which quickly gets quite tricky if you're trying to batch that together. And then also we wanted to create this kind of JSON specification for changes in model architectures that are very common, and you want to kind of change something and know that nothing else has changed in your code. So for instance, we leverage this JSON specification to be able to add Elmo embeddings to any of our models just by changing a JSON specification and not having to write kind of lots of if statements inside of models. So here you can see some of the pure PyTorch modules that you can find inside NLP. Lots of modules very specific to NLP, so conditional random fields and transformers. Here's a full JSON specification for one of our models, so you can kind of get an idea that there's lots of ways you can configure these and change them. We've got really easy to use pre-trained models, which I'll show you in a minute. We actually also have very high test coverage, and we use kind of lots of Python best practices for development, so Python 3 type hints, MyPy type checking, static type checking. So hopefully, if you take a look inside our repo, you'll find the code easy to get started with. So here's an example of what we kind of set out to do originally, which was make it trivially easy to package up a Python model, a PyTorch model specifically for NLP. So this is kind of one of the best name density recognition models you can get at the moment. It uses Elmo, and you can import this directly from an NLP pre-trained very easily and start making predictions. And here's a kind of little visualization which you can find on the our website. And the same again for a co-reference model. And these all kind of fundamentally build on neural building blocks, in kind of contrast to some Stanford Core NLP models or Clear NLP models. So now we're just going to jump to one of our actual live demos. So if you're getting bored with the talk, you can go there now and have a play around with it. So here's a dependency parser. We can type in anything you want. You'll very quickly be able to break this if you go there and start playing with it. And you get these kind of first-class visualizations of tree structures, which you can expand and play with and see kind of actually what these models are doing. And I mean, the other thing we kind of found out that when we built these demos is that it's actually very it makes where the models go wrong very clear. So here's a machine comprehension model. So there's a little passage about the matrix. So if we ask who stars in the matrix, we'll get a little span back if we're connected to the internet. Maybe we're not. There we go. So his BiDAF is great at extracting the people, and you can see little attention visualizations, which we've built in, which are really great for debugging. But then, as soon as we start to play around with this a bit, you'll see that this breaks in a fairly spectacular fashion. And this is kind of part of the work that the research that we're doing in the NLP group at AI2 is to fix problems like this. If we here we go. So, that may well be true, but it's certainly not true in the context of this paragraph. So yeah, this is the sort of thing that we're kind of looking to develop new models, particularly for paragraph understanding and semantic parsing to fix these kind of problems, because that's pretty embarrassing. So if we jump back to the slides now. Yeah, so kind of one of the main reasons we're excited about NLP is that we actually use it. So you can access Elmo from NLP, and lots of the research that we're doing comes directly out of the library, and also researchers at AI2 using it as a library, particularly from the Aristo group that work on science question answering, Semantic Scholar, which is an academic search engine, and the new AI2 Common Sense project. And then obviously we also want everyone in this room to start picking it up and seeing what it can do and seeing how it breaks. So we kind of see NLP sitting in this mid-ground between commercial NLP platforms like Stanford NLP and Spacey, but also with a lot of the functionality of things that you need for an NLP research workflow. So the dynamic nature of things like PyTorch and Dynet, and then also modern deep learning technology. Well, we use the one from PyTorch. Yeah, and then just kind of more abstractions designed for NLP, making model saving, which is more complicated with NLP models, more straightforward. We're really excited about PyTorch 1.0 because, I mean, we actually had some experience writing C++ extensions for some custom LSTM architectures, and it worked, but it was painful. And now we can just completely scrap that and go directly to just-in-time compilation. So we're really excited about that. We're also excited to see where developer tools for machine learning goes. So how type hints for Python 3.6 can be integrated into things like just-in-time compilation is kind of quite exciting. NLP has seen quite a kind of decent uptake since we launched. A mix of commercial companies and academia using it. For instance, NYU just released a big representation learning framework built on top of NLP, coming out of Sam Bowman's group, which is great. So definitely check that out if you have time. And then looking ahead, the NLP team is working broadly on out-of-domain generalization. So how can we make these models work for science text? How can we make them work for different languages? Adding new data sets to NLP, and then external adoption as well. So that's it. You can check out our demo at nlp.org. You can chat to us on Twitter there. You can install the library just via pip. And a bit of a shameless plug, we're also giving a tutorial on writing code for NLP research at EMNLP. So if you're going to EMNLP, definitely check it out. Thank you.
Okay, last session before the panel. So one of the trends we've seen in AI is really the democratization of AI learning, which is pretty exciting. Anyone can learn kind of the cutting edge, the latest, not have to get a PhD from the top university, in all deference to everyone who spoke today. What's even more exciting about this trend is actually a lot of it's being built on PyTorch. So the next two talks are actually from Udacity and fast.ai, two innovators in AI learning, and we're going to kick it off with Stuart Fry, VP Partnerships from Udacity.
Hi, everyone. I'm Stuart Fry from Udacity. At a conference all about AI, it's only fitting to go back to how Udacity started with an introduction to AI, or CS 221, taught by Sebastian Thrun and Peter Norvig at Stanford. These guys were colleagues at Google and co-professors of this Stanford course, Introduction to Artificial Intelligence, when they decided to put it online for free for anyone to take. At the same time, they were going to teach it on campus at Stanford to about 200 students. Some really interesting things happened. 160,000 people from all around the world signed up for this course, and it happened so fast that they kind of got a little bit freaked out, stopped enrollments at 160,000. The next really interesting thing that happened was that more than 23,000 people finished the online version of the course alongside the 200 folks at Stanford. And that was an aha moment for Sebastian and Peter, and really the genesis of Udacity as a company, because that 23,000 represented a scale of learning and a democratization of education. Like, that's more people than learned AI in all the other AI classes in all the other universities around the world that semester, right? Just in that one online classroom. The next really interesting thing that happened is we gave those 23,000 people the same final exam we gave the 200 Stanford students on campus. And then Sebastian stack ranked the results of the final exam, and the first Stanford exam came in at the 412th spot in that stack rank list. Now, that's not to say anything against Stanford or any of the other amazing institutions in the room today. It reaffirms something we all know, that talent is equally distributed, but opportunity is not. The opportunity to be on campus at Stanford, the opportunity to learn from Sebastian Thrun or Peter Norvig, not everybody has those opportunities. That's why we created Udacity, and that's why organizations like fast.ai that you're going to hear from exist, to make access to this kind of education broader and more available to more people around the world. So Udacity kept on making these free online courses, or MOOCs, but we also started making something we called a nano degree. Now, this is just a word we made up because we wanted to connote the shortest possible path from where you are today to this new skill set or this new job you want to be doing. And these are more rigorous than a MOOC or a free course for a couple reasons. One is they're much longer and more involved, but more importantly, they consist of projects. They're project-based curriculum. And you work on real-world projects, you submit code, that code gets reviewed by a real person with real feedback, and you keep doing it till you build this project to spec. To give you a better sense for what I mean, I'll pull some examples from our self-driving car engineer nano degree program. So for those of you local, you might recognize this strip of road. It's 280, heading south from San Francisco towards Mountain View. And for the very first project in our self-driving car program, we give students this data, and they use computer vision techniques to find lanes, and that's in the first week. So we really believe you learn by doing, and this is the first project we give you. They scaffold up in difficulty and complexity so that by about month 3, when you're working on your 5th project, you're on the same strip of 280, doing advanced lane finding, vehicle tracking. You see the car coming around the side. This is a real student project that they've submitted. And then for the final project, the 8th project in the nano degree, you give us your code, we put it on our self-driving car, and you can see this. The camera is that car driving through an obstacle course we've designed, and we've got our fingers crossed that you're ready for this project because it's an expensive car. So that's the sense. I just want to give you a sense for this. We teach by doing, and we think projects are an important part. The AI is an area we are super interested in and building a lot of nano degree programs in right now. And our School of AI starts with AI programming with Python, aimed at those with minimal exposure to coding, minimal exposure to AI. It's really an introduction to this world to get more people interested, and we think it's an important step in broadening access, getting a more diverse and inclusive set of people learning about this. And then scaffolding up to very advanced specializations in computer vision, natural language processing, even applications like AI for trading. PyTorch is an important, and increasingly more so, component of our School of AI. It is woven through 4 of the 8 nano degrees in the School of AI, and we will continue to build out PyTorch pathways as we launch new programs and update existing ones. A great example of an update we did recently was to our deep learning nanodegree program, where we did a complete overhaul and relaunch, so end-to-end PyTorch throughout that program, in addition to TensorFlow, which it was originally built in. So we really like PyTorch when it comes to teaching because you don't really have to teach PyTorch. We can focus on teaching deep learning concepts and not teaching syntax or documentation. For us, we spend a lot of time in those entry-level, early programs helping our students build up proficiency in Python and NumPy. And PyTorch fits very seamlessly, very naturally into this Python data workflow, so our students can just jump right into fun projects and iterations. Another reason we like working with PyTorch is because the partners and researchers that we collaborate with to build our nanodegree programs like PyTorch, right? So in this overhauled deep learning nanodegree program, we have a whole section on image-to-image translation, right? And so Ian Goodfellow teaches about GANs, and then Julian comes up and teaches about CycleGAN and the work he and the team did there. We look at all the creative ways CycleGAN has been used, like going from black bear to panda bear. And then, of course, we bring cats into the mix and have our students work on their own project after they've heard from these researchers and been exposed to CycleGAN models and GANs. And we give them a big old data set of ragdoll cats and Berman cats. These are two closely related species. You'll notice ragdoll cats, if you're not familiar, have that kind of upside-down triangle of light fur, whereas the Berman cats have the darker fur all around the nose and eyes. And what they do is, so we give them these data sets, and then they compress a real image and generate a fake image of the opposite species using convolutional and transposed convolutional layers in PyTorch, going from ragdoll to Berman, and then Berman back to ragdoll. Very fun project, and we like cats. Another really cool PyTorch project is this this is in our computer vision nanodegree, so a different one than the deep learning. This is an automatic caption generating project where we give students, again, a big data set of pictures and captions, and they train a CNN to recognize patterns in a particular image, and then an RNN to generate a descriptive caption of those pictures. And these are some of the results, right? Like one is my desk setup at home, a computer monitor sitting on top of a desk, or a train coming down the tracks near a station. So some really exciting hands-on applications that are a fun way to use PyTorch. As you can probably tell, we like teaching PyTorch. We like teaching with PyTorch. And so it made a lot of sense to team up with Sumith and the folks at Facebook AI. Sumith, Joe, and some other folks are going to help us teach Introduction to Deep Learning with PyTorch. This is going to be a free course, one of the MOOCs on the Udacity platform in the School of AI. And it's going to cover the gamut from an introduction to deep learning and PyTorch all the way to deployment with PyTorch and implementing your first deep neural network. So really excited to launch this course. You can sign up to get notified about when this will launch, but it's coming out on November 9th. So keep an eye out between now and then. Equally excited to partner with Facebook to introduce a PyTorch scholarship program. Applications for this program open today, and this is a scholarship challenge that'll have 10,000 scholarships globally for the first phase of the scholarship, which is a challenge program. It takes that PyTorch course, layers on some projects, then some direct support from the Udacity team and the School of AI team, and a dedicated community for a 2-month challenge as you work through the course and the related projects. Top performers from that scholarship, that phase, will get an additional scholarship, a full nanodegree scholarship to our deep learning nanodegree program that I've talked a little bit about today. All of this funded by Facebook AI. Super excited to be working with them. So the timeline is applications for the scholarship and to get notified for that course went live today. On November 9th, the scholarship program will kick off. Or if that's not interesting to you, you can just take the free course, which will go live on the 9th as well. And then the full nanodegree scholarships will be awarded in early 2019. Again, really glad to be here. Appreciate the opportunity to tell you about some of the efforts we have to democratize education, especially when it comes to learning AI. You can head over to udacity.com/fb-pytorch to learn more about that scholarship program and the free course. For those of you who have learned with Udacity, thank you for learning with us. For those of you who haven't, I hope you come check it out. We'd love to learn alongside you. Thanks, everybody.
Thomas. I'm co-founder of fast.ai. I'm really excited to be here today. I love PyTorch. So at fast.ai, our goal is to make state-of-the-art deep learning more accessible. And we do this through 4 different channels. And there's a lot of overlap between these. One of them is software. Today we announced the release of the fast.ai library, which is built on top of PyTorch. Also through education, our free Practical Deep Learning for Coders course, as well as through state-of-the-art research and a supportive and engaged community. And I'm going to talk about how we use PyTorch towards all of these goals. So software. So we have a blog post announcing the release of fast.ai version 1. This library is, I'd say, in the same spirit as Keras. It's the first kind of deep learning library to provide full support for text, vision, tabular data, and collaborative filtering all in one place. You can make state-of-the-art models in just a few lines of code. Our relationship with, and I should say you can find this at fast.ai, or you can check out the docs at docs.fast.ai. Our relationship with PyTorch goes back much further. We first tried version 0.1 of PyTorch when it came out in spring 2017. At the time, we were trying to do attentional models with teacher forcing. And these are important techniques for NLP. And we were finding it difficult in Keras and TensorFlow. We tried PyTorch and just loved it from the start. We switched all of PyTorch, or switched all of fast.ai to PyTorch about a year ago. And our reasons for that are, I love that it's a dynamic framework as opposed to a static computation graph. It makes for easier debugging, and as a researcher and developer, ease of debugging is my #1 priority. Easier debugging has resulted in more rapid iterations and easier experiments, and this in turn results in faster and more accurate models, as well as more complex models in fewer lines of code. And then a third thing, as someone who's coming from an object-oriented programming background in Python, I think PyTorch's structure kind of feels more natural and intuitive. So in fast.ai, we always start lesson 1 of our course with dogs versus cats. This is a computer vision challenge to identify if a picture is of a dog or a cat. It's been a Kaggle competition twice. And here is a comparison we did with fast.ai on top of PyTorch, comparing to Keras on top of TensorFlow. And I should note that I love Keras. The reason we're comparing ourselves to Keras is because we consider it a gold standard. And you can find more details about kind of the specifics of these tests in the blog post. But just a few lines. So we're using transfer learning here of a network that was of ResNet, pre-trained on ImageNet. Just a few numbers to note. The lowest error we could achieve with Keras was 0.8%. With fast.ai, that was 0.3%, so 99.7% accuracy. And we were able to do that in fewer lines of code and faster in less time. And these are 3 metrics we really care about: our accuracy, speed, and lines of code, the simplicity for writing it. Fast.ai has already been deployed at Fortune 500 clients. It's in use at GitHub Engineering. There was a great blog post recently on how GitHub is using fast AI on top of PyTorch for semantic code search. A senior machine learning scientist who worked on that said that this is just the tip of the iceberg. People in sales, marketing, and fraud at GitHub are all using fast AI and PyTorch. So education, who here has taken the fast AI course or watched any of the videos for it? Okay, nice. So this course is available for free online, course.fast.ai. If you're in the Bay Area, we'll be teaching an in-person version starting in late October. That's one evening a week. It'll be completely kind of newly updated. But our course takes you to the state of the art in a very hands-on and practical way. The only prerequisite is 1 year of coding experience. There are no advanced math prerequisites. And this is done in partnership with the University of San Francisco's Data Institute. Our motto is making neural nets uncool, because being cool is about being exclusive. And our goal is to make the field more accessible and more inclusive. So a number of our students work on social impact projects. There was a great Forbes article about several of our students around the world working on social impact projects. This covered several students, including Sahil Singla. Sahil worked with Farm Guide in India to develop better agricultural lending models for farmers. Most farmers there can't prove how much land they own or what type of crops they're growing. And using publicly available satellite data, Sahil and his team could develop better lending models. The other great thing about this article is that it was written by a fast AI alum, Maria Yao. Maria is the author of a best-selling AI book, as well as CTO of MetaMaven, and just won an NSF grant, despite not having a graduate degree. And then while we have a lot of social impact projects, we also have a lot of more playful projects. Tim Onglade was one of our students. He works for the HBO television show Silicon Valley, and he built the Hot Dog, Not Hot Dog app while taking our course. And he was nominated for an Emmy for this work. A fun project that came out recently from Christine McLevy-Payne, she's a Fast AI alum who went on to become an OpenAI scholar, is a neural net music generator. Let me play a little bit. So this music was written by a neural net. Christine has a background as an award-winning classical musician, as well as a high-performance computing expert. You should check out her blog post, but she wrote this using fast AI and PyTorch, and she said one of the things she loves about fast AI and PyTorch is how flexible they are, and she was able to repurpose code that had originally been written for natural language. So research, we're really trying to disprove the myth that you need the fanciest, most expensive computers or the fanciest background to do state-of-the-art work. Earlier this year, a team of fast AI students competed in a competition hosted by Stanford against engineers from Google and Intel who had a lot more funding and more expensive computational resources, and fast AI won, which is really exciting. This was covered in The Verge and the MIT Tech Review. But I'm really proud of this, and also just to show that, that anyone can do state-of-the-art work. And then this is some research from a co-founder, Jeremy Howard, who will be speaking next, along with Sebastian Reuter, that came out earlier this year applying transfer learning to NLP. So we've seen a lot of breakthroughs with the use of transfer learning for computer vision. It's much newer for it to be applied to NLP. And you can find this work on the archive or a layperson's version at nlp.fast.ai. And again, this was using fast AI and PyTorch, and they achieved state-of-the-art on 6 text classification tasks, in many cases improving it by 18 to 24% over the previous state-of-the-art. And then we're fortunate to have a really supportive and engaged community. You can check out on our forums. There are people always asking for help, offering help, sharing interesting links or projects. And I wanted to highlight just one forum thread in particular. This is the Language Model Zoo, and this is a thread of people applying Jeremy and Sebastian's work to languages all over the world. And it was almost too much to fit on a single slide, but Bengali, Chinese, Danish, Estonian, Finnish, Hebrew, Hindi, Italian, Indonesian, and there are more. And in this thread, people are sharing best practices and tips, also linking together in groups to work on it. I particularly want to highlight the teams working on Polish and Thai for achieving state-of-the-art in their languages. The group in Polish won the top Polish NLP competition, and Polish is a morphologically rich language, which means it can be pretty challenging for NLP. But so this is an interesting resource if you're interested in that. Yeah, so finally, just thank you for having me. I am so excited about where PyTorch is headed and have really, really enjoyed the event today. And be sure to check out our new fast AI software library. Thanks.
My mic on? Okay, hi. So, it's been a long day. It's been a really long day. And the final session we have is having a small panel to discuss from a set of very opinionated people what the future of deep learning software, the software of the AI stack itself would be. And then we're going to have a great poster session with 40 posters, I think 40-ish. And so let me start off with the invitees for the panel. The first one is my homeboy, Yanqing Jia, who is Director of Engineering at Facebook AI. And you might know him as the creator of Caffe, Caffe 2, Onyx, and also now part of creating PyTorch 1.0. And the second person on the panel is going to be Noah Goodman, who is an associate professor at Stanford, where he runs the computation and cognition lab. But he also runs the probabilistic team at Uber, which built Pyro that you saw talk about. The third person on the panel is Jeremy Howard, who built fast.ai along with Rachel, who just spoke to you. And Jeremy was also the CEO of Enlitic, which was a medical imaging company. And before that, you might know him as the president of Kaggle, which I don't need to introduce to you what Kaggle is. And the last, but definitely not the least, panelist is Chris Latner from Google. And you might know Chris by accidentally using LLVM or CLang, or as the person who built Swift. And also, he led the developer tools group at Apple somewhere around that timeline, I guess, where he built Xcode, which, again, you probably are very, very familiar with. Without further ado, I invite the panelists to come onto stage. So some questions are going to be a little hard to answer, and some are easy. I'll start with an easy one. Let's say each of you goes to a party, and you have to tell someone what field you work in. Do you say artificial intelligence or machine learning? Starting from right to left with Noah.
I say human and machine intelligence.
Human and machine intelligence. That's a good answer.
I just say AI. I don't like the term, but people know it.
I generally say ML for no particular reason.
Yeah, I'll probably do AI.
Okay.
ML is a little bit old-ish, but it's awesome.
Nice. All right. That was easy. Now, to get into depth of, I mean, the panel was about the future of AI software. I want to ask you're really talented people on the panel. I want to ask your opinions on what the future looks like. One of the things that the Python data ecosystem has done is basically eat up every machine learning framework, especially deep learning framework. And now Python is pretty much the only language in which you can do sensible deep learning. How do you think this would change over the next few years? Do you think there's a good way to introduce a new language if it's the right one?
Sounds like a waste of time to me. Of course there is. The only bad thing about PyTorch is the Python bit. Python's, you can say about Python that it's better than R, but it's worse than everything else. The fact that PyTorch makes it nice is an extraordinary effort on your part, Sumit.
So
I think you're aiming this at me, I can feel. So I can honestly say I don't know, right? I mean, I think the Python ecosystem has a ton of great things. I don't really look at it as an ecosystem language, other piece. To me, I start with what are the goals, right? And for me, I personally am one of the people that believe in big data plus big compute plus good algorithms leads to progress, right? And for me, it's about the dream of the interactive supercomputer. Like we have today very large boxes that do 100 petaflops today, right? That's a thing, right? And driven with that kind of compute power, you can solve really interesting problems. And so Python at scale leads to some challenges with performance, the GIL, lots of things that drive poor usability. And to me, interactive supercomputers are really about being able to take theoretical flops and turn them into practical applied flops that solve problems, like turning people into more effective and more productive engineers and scientists and other people that are just solving problems, right? I think that people neglect the joy part of programming and solving problems, but to me it's super important. And so what Swift is about, and Swift for TensorFlow is about saying, well, you know, a lot of the ideas and a lot of the way that frameworks have been built have been kind of limited by what can we fit into Python, right? And I'm saying, okay, well, this is actually a hard problem, but what if we just like rip the cover off and say, let's change the language as well? Well, if you do that, and if you look at that, and then you say, what do you want? Well, you want things like amazing autodiff, like that's super extensible, so you can define your quaternion type or whatever else, and define custom gradients. You can do gradient surgery. You can do like all the things that people have known and loved 40 years ago in the Fortran world, but that we as an industry have somehow forgotten, right? And it's because you need really good language integration. And once you do that, the error messages you get, the experience you get of using this thing can be really great. And it's also completely orthogonal from tensors, but tensors are a really important application.
And you don't end up down at some layer where you can't dig any deeper, and you go like, oh, yeah. At that point, cuDNN takes over. Like
right.
if it's Swift all the way down, that would be so cool.
Right, and so like on a programming model perspective with tensors, kind of the Swift way of looking at this is saying, well, eager execution is a good thing. That is really the right answer for so many reasons, right? But the goal here is that the system should be able to be in charge of giving you good performance. And so the way the Swift for TensorFlow model works is you can think of it as just being a really fast eager mode with a concurrent, very fast base language. But then when you turn on the optimizer, it does auto clustering for you. And so now you get graphs, large-scale graphs, that you can feed a supercomputer, and it just kind of works, right? And yet, if you want to be able to step through your code or set a breakpoint, fine, you compile with O0, and then you do that. There's no things to move around, and so you get a very nice continuous experience. The Python ecosystem is super important, and it's not going to change. And so with this model, you can just import Python APIs and use them directly. No FFI, no wrappers, no build steps. You just use Python in all of its dynamic glory, and it just works. It's super nice. So there's a lot of kind of thought been put into this, but there's really that question, which is the social question of, will the world be ready for something that's not Python? I don't know. It'll be really interesting.
Okay. Noah, as someone who built your previous software in JavaScript, how do you feel about it?
Well, I love JavaScript, not as much as I love Scheme, but more than I love Python. Yeah, so I think Python is here to stay for a while just due to the intellectual economics. But the remarkable thing about it to me is that Python is this thing where the more of your libraries you don't write in Python, the better your Python libraries get. That's why PyTorch does such amazing things by pushing everything that's useful into C++. And I think that's indicative of the eventual future, even though we're at a local optimum where it's very hard to escape the goodies that Python gives you.
Okay, interesting.
So I think a lot of folks have talked about the pros of Python. And I think the con of Python that people often talk about is the speed, like it's run slowly. And that's actually one of the key reasons Python is really good for machine learning, because when we go to machine learning, then we found out that the computation is very bulky. We run a convolution, we run machine applications, milliseconds, basically. And adding a 50 nanosecond overhead is not too bad. And then basically, that's a very good fit and a pretty good trait for flexibility and being able to tinker around with all kinds of stuff. Like one example is my wife is an economist, and it's really hard for her to learn C++. I tried, failed. She's doing Python very happily. And that's kind of like the flexibility that if we bet that machine learning, or PyTorch hopefully, is going to be the Starbucks of the machine learning world, then that's kind of some flexibility that we need to provide to the users. And my wife hasn't started learning PyTorch yet, but hopefully she will one day.
Soon. Yeah. Everyone needs to use PyTorch soon.
Hey, Sumit, you don't get to skip it, man. What do you think? I'm really interested. Do you think there'll be a Swift torch? Do you think Python's the way we'll stay?
There's a reason I wanted to be moderator. I don't know the answer, but I'll do whatever people ask for. So we'll see. We'll find out. So that was good. That was very helpful. So the next thing I want to ask is, so one of the things that's happening is every day, every month, the AI landscape is changing, and we have new models. Like transformer models didn't exist like too long ago, and now they're everywhere. Some people say probabilistic programming will be like the next wave after deep learning. And if that happens, I mean, first of all, do you guys expect that to happen? Something like probabilistic programming being at the center of the next wave of research for mainstream applications. And if that happens, how do you see the software stack changing? Do you see DSLs coming about? Like, what are your opinions? Maybe starting from the obvious person, Noah.
Yeah, so the obvious answer is, of course, probabilistic programming is the next big thing that will take over the world and eat your lunch. And that's true, but that's not actually the interesting part. I think the interesting part is that we're seeing a multi-paradigm programming. So differentiable programming over here is why we're all in this room, and it's amazing and doing good things. Probabilistic programming was over here, and now it's kind of overlapping over here, and that's the hypothesis we're exploring with Pyro. I think that's what's really exciting, and that's the thing that's going to take over and change a lot of things. So there are cases where you really crucially want to think about probabilities and latent random things that basically give you explanations of your data. Sometimes you don't, sometimes you do, but only a little bit. And so systems that are able to fluidly express those different concepts, as well as other paradigms like logic programming maybe, I think that's probably going to be the thing. But not for a couple of years, because we have to really figure it out before everybody's building their new random Googles on it.
Only a couple of years? All right. Jeremy?
Well, yeah, I mean, long time ago, 20 plus years ago, I was very into what was then called systems dynamics, which is kind of the closest thing to what's now called probabilistic programming. It's actually very close, and it was huge for quite a while. There was a huge center at Accenture focused on systems dynamics, and there was all kinds of plugins that you could get for your spreadsheet for it. And so I've been a fan of it ever since. I think the current methods are really overcomplex in the same way that current deep learning software is overcomplex. I think they both offer the same thing, which is machine learning should be about having your computer solve your problem for you by giving it examples, which shouldn't require any code at all. Probabilistic programming should be about you providing your domain expertise to say, okay, there are some pieces of this puzzle where I have some belief about what will happen and how likely it is to happen and what kind of the shape of that happening is. So these are things that they, should be highly accessible to domain experts. And so the other piece to me is combining it with what we saw earlier, which is the domain-specific differentiable layers. I think these three things together hopefully will get us to a point where regular people, maybe not coders at all, can use the information they have, their knowledge, to create, solve a problem and get back, accurate predictions and recommendations and confidence intervals.
Right.
I don't have the depth in probabilistic programming, but I generally completely agree with Noah. And my view on it is that it's too easy to look at things as being, is this going to win? Is this going to eat and solve all problems? Will deep learning solve all problems? Well, solve a lot of really interesting ones, but not all of them. And in the old days, people would argue, isn't functional programming a better way of doing things? And the answer is yes, it is better at certain problems. And ML is amazing at certain problems, and probabilistic is good at certain problems. And the question is, how can you pick and choose the problems and use the right technology, make it easy to use, build the right abstractions, build APIs and systems so that people can pick and choose the technologies without having to completely switch to a new tech stack to use it if it's the right thing. But I look at it as very much, what is it good at, what is it complementary with, and how do we compose these these things together?
Got it.
So to add to Chris's point, basically, I remember back in maybe 6 years ago, back at Berkeley, there was this project called Gibbs LDA, where probabilistic graphical model was really popular back then, and everyone is basically drawing circles and connections and stuff like that in the papers. And one thing that was really similar back then and today is that in the project of Gibbs LDA, we basically worked on using GPUs, CUDA actually, to accelerate the computations and make things really high performant and distributed training and stuff like that. And that basically made the project executing really fast. While nowadays Gibbs LDA or LDA itself is probably not as popular as it was today. I hope it will come back a little bit later, because that was one of my PhD projects. But the things that we learned is basically we need to build software that can be shared and can be basically built upon. And instead of basically building little research code that we basically send around in email attachments with zip codes without versioning, and we basically just hope that someone is still holding on to a version of the code that runs a version of our experiments. And that kind of plugs back to Andre's earlier comment today about software 2.0. And over the last few years in the machine learning community, I think what we learned is that we need to put proper software engineering practices in our research and product pipelines.
Makes sense. Yeah. Great. So leading on to one of the things that everyone talks about these days is faster and faster and faster hardware, and what are the consequences of that? What's happening is not just faster hardware, but hardware is also becoming less general purpose and more focused on deep learning, right? So do you think there are adverse long-term effects to the field of machine learning research if this trend continues? And how do you see the software stack changing?
Do you mean too much specialization in terms of hardware, or what do you mean by that?
Adverse or non-adverse? By adverse, I did mean if it's too locally overfitted,
I see.
What's going to happen to the global searches? But there could be positives as well. If it's the right model, then you accelerate progress as well, right? Any thoughts on how the software stack changes? What do you think the field is?
It definitely changes things, right? GPUs have had this massive effect. They weren't made for deep learning, everybody knows, but they've had this massive effect because they provide one set of operations that goes super fast. If somebody had happened to make, some other thing that happened to make parsing in context-free grammars go super fast, we would all be doing deep grammars or something like that. So yeah, it'll have an effect, but I kind of think that the research community always escapes those local optima eventually. So the more we overfit to this particular class of things and build our hardware and software, the more there's the opportunity for a really great PhD thesis or a really great startup that jumps out and is like, oh, actually, so it's an effect, but I'm not pessimistic.
Okay.
Yeah, I mean, it's interesting, Sumit. Like I've noticed throughout my career, consistently, all the people around me are talking about how we're at a step change in massive data, massive compute. So I've been hearing that for 25 plus years. And as a result, which is natural, right? Because when you see hardware improving exponentially, it always feels like a step change. That that last 2 years is more than the previous 10. So I always, to me, it's a terrible distraction. It means that most of the engineers I've known working around the machine learning field throughout that time are focused on taking advantage of as many machines as possible and as much resources as possible, which, as we all know, there's a lot of overhead to that. Instead, I would strongly suggest to people that pull back and think, like, what can I do on my laptop now? Because now you're focusing on, so for now, right now, I think something that not enough people are working on is what can you do in JavaScript? Because now you don't need an NVIDIA graphics card, you don't need to install anything, you can have something running in everybody's browser, they can start playing with it straight away, and you're working with something that 10 years ago was the giant room of computers. And it's when you're working under constraints that you do amazing work. So, we've tried to publish as many pieces as we can showing, hey, did you know that you can train ImageNet on AWS in 18 minutes for $40? Did you know that you can get a state-of-the-art text classification in 3 hours on a single GPU? Did you know you can, replicate this state-of-the-art result in 3 lines of code? It's, to me, it's all about simple, fast, cheap. I think there's not enough people working on that problem, and I think it's the more interesting one to me.
That's interesting.
I have a little bit of a different perspective, I guess. I mean, I agree with what you said, but I'm less concerned with the overfitting on hardware and more concerned with the overfitting on software.
Okay.
Like, if I look out at the industry, there's an explosion of hardware going on. Like, it seems like every startup is making an inference chip, and every new phone has 2 or 3 or accelerators built into them. If I look out there, I see JPEG decoders that are accelerated. I see GPUs, obviously, TPUs. There are a tremendous number of these things, and the hardware is moving much faster than software. And I think that's happening for a number of reasons. One of which is the end of Moore's law, which is widely blamed, but it's actually true, is causing specialization of hardware to become much more profitable in terms of the way to get performance. And it's not just matmols. It's also JPEG decode and many other things that are previously not important enough to accelerate become important, and particularly in high throughput inference scenarios or other things like that, it's actually a critical bottleneck. And so, to me, I'm a bit concerned about the software stacks that are say, well, ML or AI is all about matmols and convolutions, so we'll accelerate those, while ignoring the sparse embedding lookups, ignoring the JPEG decode, ignoring the image augmentation, other things like that that feed the machine, ignoring the I/O subsystems that you have to pipeline in order to get decent performance. And I think that holistic software is necessary to enable this. And once you do that,
often ignoring the developer user experience. I mean,
yes.
You and Sumit are maybe
yes.
2 of the 3 people doing a great job there,
yes.
but not really widely
yes.
studied.
Well, and I mean, I take the perspective from the compiler lens of matmols and convolutions are really disproportionately important, right? I mean, they're really, really, really important, but they're not enough. And you need to care about the whole stack and be able to cover the whole stack, and then be able to invest effort in the things that happen to be disproportionately important today to get good performance without giving up generality. And I think that on machine learning models, the trend line is towards generality. Like, we're still struggling with control flow, right? But generality and tree recursive neural nets and like many of these other things are just not being tapped into because the software stack doesn't make it easy enough. PyTorch is exceptional in this case, but
Thanks.
So actually, out of curiosity, when we talk about the proliferation of different hardware pieces, is it possible that all those hardware pieces that we build in today is specifically just trying to optimize CNNs and RNNs, or maybe measurement allocations, or are we actually having hardware built to deal with like decision trees or random forest or sampling or things like that?
Well, so I think that people, again, there's this focus of attention that people like to think about GPUs. And like to think about TPUs, or they like to think about different applications because that's what they're charged with thinking about. But it turns out, again, each of these are really good at solving different problems. CPUs are really good at walking trees.
Pretty good, yeah.
Right? And they're actually like designed to be really good at that. And what we need is software systems that allow models to be continuous and take advantage of the already heterogeneous accelerators that we have.
Right, that makes no sense. Actually, like one thing that I kind of wonder is it mainly because the hardware evolution is actually way longer than the software evolution path? Because we're joking that we burned through like maybe 20 different deep learning frameworks over the last 5 years, and we've probably seen like a couple generations of hardware, and NVIDIA have been doing a really great job on the GPU side, but we haven't really seen too much like varieties of different hardware coming up. So maybe it's also kind of like try to see how we can do similar to throw away software, to throw away hardware, so that we can do, like, imagine if we do a new chip in the data center every month. That will probably be very different from what we have today.
So you should look to mobile, because they like literally want you to buy it and then throw it away 2 years later.
Exactly, yeah.
Right, and so if you look at mobile, I think that there's this explosion of accelerators, and it's not just mobile phones, it's also things like VR headsets and cars, and like this edge thing that like it's labeled is actually really complicated and really interesting too.
Right.
But Chris, even in hardware, it feels in some ways like the innovation has gone away or slowed down. Like when I see all of these explosion of hardwares, they tend to be digital matrix multiplication units, where maybe the innovation is how many bits we use and how those bits are laid out. But like in the, when was it? Well, early 90s, Intel was selling a mass market analog CPU. And unfortunately, they had to shut it down because, you know, I guess the people trying to write the software couldn't quite figure out how to deal with temperature issues. But I'm thinking, like, what if, like, you know, Intel was releasing a analog CPU today where we were getting, you know, or just an approximate CPU,
or
like
quantum.
Well, okay. I
like
mean,
or optical, right?
Well, now optical does exist. Yeah,
I know.
There are some
like people are working on all
doing
these
optical, and they are great. But I do think, yeah, I wish this explosion of kind of AI hardware companies were doing more things than low-bit digital matrix compute. It seems a bit short-sighted to me, because it seems obvious it's not the right way to.
But on the bright side, I actually think AI is very likely to drive that novel hardware explosion eventually, because we're very much myopically focused on, you know, oh, look at all the things we can solve as long as we have huge data and huge power. But pretty soon we're going to have to deal with, like, you know, this thing up here does the same thing with pretty small data and very low power, right? Yeah. And when we start focusing on that, it's going to, I think, drive those hardware
about 10 operations per second at most for each unit.
Yeah.
But incredible parallelism.
Yeah.
I just want to like throw in the point that spiking neurons is probably another example where we can do hardware, but the software side is not really ready, or like we don't even know how to actually train a spiking neuron.
Great. All good answers. I know a lot more now about what's going to happen. So one of the next things I wanted to ask was, in the last couple of years, from my memory, hyperparameter search using neural networks, whether you take it AutoML or there's a series of researchers trying to search for our neural network architectures themselves or better hyperparameters, and like there's traditional Gaussian processes-based stuff that's being revived in this AutoML paradigm, which has become a bit more popular. If hardware, as you guys say it, with optical processors or whatever, or the magical processors, becomes like 100x faster, 1000x faster, do you think that combined with the AutoML stuff that's being popularized would change the way people do both research and or build products in AI?
Yes.
I think so. I think I can probably provide one example. So, like, when we're learning programming languages, we have this notion that, like, object is a class an object in Python, right? And we're like, what is that? And it's kind of the same thing. Today, we deal with data, a massive amount of data, and we distill models out of that. But one thing that's interesting is the models themselves, or the way we train models, become data themselves for us to basically then train mechanisms, semantics, or rules and principles for us to improve the models. And one particular example is, today we are doing a lot of compilers and optimizations. I'd love to get Chris's view on this one as well. We run them, and we do optimization by heuristics. There's a bunch of rules that we derived, saying if we run O2 or O3, these are things we can make it faster. If we're running machine learning models, today, for example, like Jerome mentioned that for a bunch of models, we run 300 trillion predictions per day. Imagine if we can collect in some way profiles of those executions and then get some more heuristics using reinforcement learning or whatever approaches for us to do a more profile-based or data-based optimization. That would actually open the gate for a lot of new technology that we were probably thinking about but couldn't do in the past, and hardware would probably make it much easier as well.
Mm-hmm. Yeah, I definitely agree with that. I mean, I think, to me, I look at this as there's multiple different phases and different kinds of opportunities here. As you say, like, compilers are full of magic knobs, and should I inline this function? Well, magic number, heuristic, hard-coded, tweaked, tuned, completely the wrong model, right? This is the old way of building things, and LLVM, for example, is roughly 20 years old, and it shows it, right? And there's better ways of building compilers these days. But I think that your bigger question is AutoML the right answer? Is ML development going to be taken over by the machines? And I don't really know, obviously, but I look at it as it's another tool in the box. And there's a certain class of people that are not going to know and understand differential programming, and they won't understand the basics of ML or models or things like that. And I think that AutoML is a great way of bringing that to more people and bringing it to people that have data and have problems, but they don't have the expertise. I don't think it will be the closest fit necessarily to solving the problem, and so if efficiency really matters, then it may not be the best answer. But when you combine that with the explosion in compute that's happening, I think that the only question is where do these lines cross over? I was inspired by Andre's talk with the Software 2.0 thing. I think that if you think about what if you could do your development and have like continuous integration of every label update and see what it does for all of your metrics and get that in the loop for people doing labeling, that would be huge, right? And these kinds of workloads are only made possible by dramatic amounts of computes, good integration, good software layers, and all the things designed and working well together. So I don't think that all programmers are going to be out of a job, at least in the next 5, 10, 15, 20, I don't know how many years, but I think that I see it as AutoML is a great way to open the field and open the technology to new people.
But you're right, it really is two things, right? One is as a specific tool so that I don't know what that knob is, figure it out for me. And that's the sort of thing you want your AI IDE to be able to do. But the other thing is really like, the pie in the sky general AI sort of step of I like to call this inference bootstrap, right? When you can pose the problem of making your inference algorithm better as an inference algorithm and actually apply it to itself. Oh. This is a call out to the old Fudamura projections for compilers, right? Yep. Then all of a sudden, you're in a completely different world where you can step back and, hypothetically achieve great things. That's not at all about the current hardware or the tools. That's like a vision that someday may come to pass if we're all lucky to see it.
So can I just put it out there and say, I think the problem of getting rid of the knobs is a problem to solve. I think AutoML is totally the wrong way to solve it. I mean, 25 years ago, you could buy a piece of Windows software from the mass market that would grow a neural net for you dynamically. We're not using it today. It didn't go anywhere. Why not? Because at any point, you can figure out a few heuristics and rules of thumbs to get really good performance without having the machine try every damn thing. Like the very idea of the word AutoML, it shouldn't be auto. It should be augment ML. How do we get the human and the computer working well together? So like, this is why I would much rather use Leslie Smith's learning rate finder that tries a few batches, finds the learning rate that works, and then you can look at it and pick one, rather than have 100 TPUs try every damn thing. And we're now starting to work on extending that to regularization methods. So to me, it's all about like coming up with smart, thoughtful, well-curated approaches rather than think, let's just get the machine to solve everything. Because anybody who's working on the let's get the machine to solve everything problem, the people who are working on the curation will always kick their ass. They're always going to have something that's faster and better at any generation of hardware. So to me, that always wins.
Just because they always have doesn't mean they always will.
It doesn't mean they always will, but I don't see why it would change, because at any point in time, there are reasons that a particular learning rate makes sense, or a particular amount of regularization makes sense. I think the architectures should be developed largely automatically, but once for images, once for handwriting, once for language models, and then we can all use it. They're too hard, but the hyperparameters, they should be things that we have thoughtful rules about, how to pick them.
I think that's the secret. When you see the thing and you're like, actually, that's too hard, that's when we need more. I'm not sure AutoML per se, but meta inference and meta.
Yeah,
ML.
but let's get rid of the grid search and Gaussian process and all that stuff. I think that's silly, personally. It sells lots of computing hours, so it's good for the cloud vendors.
Yeah. Great. So we are out of time, even though I want to ask a lot more questions. It's not often you have a panel like this come together. But because we are out of time, let's thank the speakers and yeah.
Oh, one last couple of comments. Sorry, guys. So first of all, I know everyone's excited to leave. Hopefully this was awesome. Was this cool? So thank you to our speakers. Thank you for everyone on the live stream, in person. Thank you to the PyTorch core team. I can't name everyone because it's a really, really, really long list. And actually, most importantly, thank you to Bruce Lin. So everyone thank Bruce Lin because he's the one who actually made this conference happen. He's awesome. And let's convince him to do another one next year. And just last couple things. So one, check out the preview again. So give us feedback. Tell us what sucks, what's awesome. So we fixed it. Jeremy Howard, I think, already has pull requests in or filed issues. So he's incredibly fast. Just like the, yeah, anyways. All right, and logistics. So time to drink. So there is a bar here. There's a bar over there. In the middle, there are about 40 posters, so check them out. There's going to be a DJ. Everyone inside is vowing to dance, so have fun. Enjoy the rest of the evening. Connect with someone. And see you guys next year. Cheers.